Now, let's talk about the actual hands-on process. At this stage, we are taking our cans, filled with the moist soil directly from the field, and placing them on the balance. What we are looking for here is the total initial weight. Think of this as our starting line. By recording this exact weight right now, before any moisture has a chance to evaporate, we establish a reliable benchmark. Later on, after the oven drying process, we'll contrast this number with the dry weight to figure out exactly how much water that soil was holding. Once we have successfully recorded the initial weights, we move on to the thermal dehydration phase. We are now setting our laboratory oven to the standard temperature of 150 degrees Celsius to ensure complete moisture extraction without burning the organic matter in the soil. After allowing the oven to reach its preheating phase and stabilize at this uniform temperature, we carefully place our soil samples inside. The samples will remain in the oven for an hour. This waiting period is critical, as it ensures the soil dries to a constant mass, completely evaporating the pore water so we can later determine the true dry weight. Once the drying cycle is complete, we enter the final analytical phase of our experiment. We are now carefully removing the dry soil samples from the oven. Before we place them back on the scale, it is standard practice to let them cool briefly, ideally in a desiccator, so that convection currents from the heat don't interfere with the accuracy of our balance. Once cooled, we measure the final dry weight. By comparing this dry mass to the initial moist weight we recorded earlier, we can calculate the exact mass of the water that evaporated. This difference gives us the precise gravimetric water content of our soil sample. We use this specific formula because soil is fundamentally a mix of solid particles, water, and air. When we talk about soil moisture content, or water content in civil engineering and geology, we want to know the ratio of the weight of the water to the weight of the solid soil particles alone. Here is a breakdown of why the math is structured exactly this way. The top part, moist, MDRY, isolates the water weight. When you pull the soil out of the field, it has water trapped inside its pores. Moist is the weight of the soil solids plus water. MDRY is the weight of just the soil solids, since the oven completely evaporated the water. When you subtract the dry weight from the moist weight, the soil solids cancel out, leaving you strictly with the exact weight of the water that was lost to evaporation. The bottom part, MDRY, serves as a stable baseline. In geotechnical engineering, we always divide by the dry weight, MDRY, rather than the total wet weight. Why? Because the amount of water in a soil sample changes constantly depending on the weather, compaction, or environment, but the amount of solid soil particles stays exactly the same. By using the stable, unchanging dry soil weight as our baseline, we get a reliable, standard ratio that can be used to compare different soil types accurately. And the we multiplying by 100. This simply converts the decimal ratio into a clean percentage %, which is the standard way moisture content is reported on datasheets and engineering reports. In engineering, construction, and agriculture, soil isn't just dirt, it is a critical foundational material. Determining its moisture content is one of the most fundamental laboratory tests because water completely changes how soil behaves under pressure. Here is why getting the moisture content is so important and what its main purposes are. 1. Compaction and structural stability. When building roads, foundations, or embankments, soil must be compacted using heavy rollers to press out the air pockets. If the soil is too dry, the friction between particles is too high, and it won't compact properly. If the soil is too wet, water fills the voids, and you end up just pushing mud around. The purpose: knowing the moisture content allows engineers to find the optimum moisture content. This is the exact, sweet spot, percentage of water needed to achieve the maximum dry density, ensuring the ground is strong enough to support heavy buildings and highways without sinking later. 2. Predicting soil load-bearing capacity. Water acts as a lubricant between soil particles. When moisture content increases, the cohesive strength of the soil decreases. By measuring the water content, engineers can calculate the soil's shear strength and load-bearing capacity. This prevents catastrophic structural failures, landslides, or severe foundation settling. 3. Identifying expansive soils, shrink swell behavior. Certain types of soil, especially those high in clay, act like a sponge. When they absorb water, they swell significantly, and when they dry out, they shrink and crack. The purpose: tracking moisture content helps identify if a site has highly expansive soil. If built upon blindly, the shifting ground can easily crack concrete foundations, rupture underground pipelines, and buckle pavements. 4. Soil classification and behavior, Atterberg limits. Moisture content dictates the state of a fine-grained soil. As soil transitions from dry to wet, it passes through different states: solid, semi-solid, plastic, moldable, and liquid. Engineers use moisture content to determine these boundaries, known as Atterberg limits, which tells them exactly how the soil will behave when exposed to heavy rain or drought. In summary, we measure moisture content because water dictates how soil behaves under a heavy load. Knowing the exact water percentage tells us how well the soil can be compacted, how much weight it can safely support. and whether it will dangerously swell or shrink when environmental conditions change. Essentially, it ensures the engineering foundations we build remain safe and stable.